Hello, this is the second class of central orbit. This is a continuation of the previous class. Today we'll discuss about few problems and few concepts. Prove that first one is prove that if a particle moves in a central force field, then its path must be a plane curve. So the proof is that you take the same diagram. The F is the force towards O and P is the position of the particle at any time t, and let the force is a function of r, and along that direction r1 is the unit vector in that direction of the position vector r. Then r cross f would be 0 because r is the unit vector. That is, we can write r1 as r by mod r modulus r. Again we know f is m dv dt. So if you substitute, if you take the cross product, then r cross dv dt equal to 0 vector. So naturally we have ddt of r cross v equal to 0 vector. On integrating, we have r cross v equal to h vector. H is a constant vector. So this is if we substitute in multiplying both sides of 4 by r dot, that is taking with dot product with r, then r dot h is equal to 0, as the box rrv equal to 0, as the box product of rrv equal to 0. So this is nothing but the equation of the plane, equation of a plane. R dot h is equal to 0. So r is perpendicular to the constant vector h. That is proved very easily. So we can conclude that the motion takes place in a plane, and in this case we always take xy plane is that consideration. Next we shall prove for a particle moving in a central force field, the angular momentum is conserved. So what is angular momentum? Moment of momentum. Okay, so from the previous result we have r cross v equal to h vector. So naturally m r cross v equal to mh. So what is the LHS? LHS is nothing but your angular momentum, because mv is the momentum, and with respect to if you take the cross product with respect to r, it will give you nothing but your or momentum, moment of momentum, that is angular momentum. So and on the right hand side you have a h as a constant vector, m is also constant. So it's naturally it's give you one step proof that angular momentum is conserved, that is always constant in magnitude and in direction. This is also a very important result, that r theta dot is equal to 2a dot. What is a dot? Where a dot is the time rate at which area is swept out by the position vector r. So there is a diagram, three-dimensional diagram. Suppose that in time delta t, so this is the this is OM is the r vector, and in time delta t let n be the position of the particle, that is the particle moves from m to n. So that is given by delta r. The area delta A swept out, this area I am talking about, this area. So this area is swept out by the position vector in this time is approximately half the area of the parallelogram. We know that from the parallelogram law. If you take the parallelogram law, then we can write delta is nothing but your half of modulus of r cross delta r vector. If you take limit delta t tends to 0, then delta A by delta t equal to this, and this gives you half r cross v, because v is dr dt. So dA dt can be written as a dot half r cross v, and also we know that a dot is half r square theta dot, that is from the previous results. So we are using r cross v is equal to h vector, that is constant vector. So a dot, what is the a dot? A dot is the rate of, a dot is nothing but your dA dt. So we prove that swept out the area, the time rate at which area is swept out by the position vector r is nothing but your half. Also, we can prove that for a particle moving in a central force, the area velocity is constant. So r square theta dot is 2a dot. That is already we have the result from the previous proof. So if you take the vector in vector form, we can write this is the unit vector in the direction of a dot. Let us see the diagram. So this is your areal velocity direction of the, we know that cross product is perpendicular to the both the vector r cross v. So this is the direction of that vector a dot vector k vector in that direction. So we can write a dot vector as a dot k cap. Also we have a dot from the previous result, r half r cross v. So we write half r square, because r square theta dot is equal to h. We know that from the proof of the differential equation of the polar form, r square theta dot k cap. So r square half r square theta dot, we can write half h k cap. So this is nothing but your h vector, constant vector. So we can conclude that if a particle moves in a central force field with O as center, then the radius vector drawn from O to the particle sweeps out equal areas in equal times. This result is sometimes called the law of areas. Okay, so there are some few proofs, very small proofs. You can go through this. Let's have some problems. How to deal with the problems? First problem, a particle describes a path r to the power 4 a to the power equal to a to the power 4 cos 4 theta. So I want to recall the differential equation. For the solution, what do we have to find out? Find the law of force and the velocity of at any point, So I want to recall the differential equation of the path in polar form. So this is the polar form, and this is the pedal form. This is the pedal form, already we proved in the previous class. So it's very simple. You have a relation like this. You take a log on both sides and differentiating with respect to theta. You have r d theta is equal to minus cot 4 theta. You can easily verify that. This is the diagram. Again we have to draw the diagram. So P is the position of the particle. You know that small p is the perpendicular on the tangent from O, and you know well known relation is tan phi is equal to r d theta dr. So we can write tan phi is equal to minus cot 4 theta. So the value of phi can be find out. Phi is equal to pi by 2 4 theta. Also we have P is equal to r sin phi. This is also a known relation from pedal form, and after substitution we have this value of P as r to the power 5 by a to the power 4. So differentiating with respect to r dp dr, that gives you dp dr. Substituting in 2, that is the pedal form, it gives you f as mu by r to the power 11, where mu is nothing but the constant 5 h square a to the power 8. So this is the constant value. So what is the law of force? This is the final law of force. A varies as 1 by r to the power 11. So this is the law of force. Now what is the velocity? Yeah, there is a very well known relations for the velocity. V square is equal to a square by p square. So you substitute, you will get the velocity in this form. So this is the solution of the first problem. Let us discuss about the second problem. The same thing, but we will have a different approach in this case, taking logarithm. We have a lemniscate of Bernoulli's, that is r square a square cos 2 theta. In this case also we have to find out the law of force. This is the question. A particle describes the second or central orbit under a force towards the pole. Find the law of force. So r square is this. We know r is equal to 1 by u. This is the standard substitution. Taking logarithm on both sides, we get this result. Differentiating with respect to theta, du theta. This is a different approach, not like tan phi we have done in the previous problem. Again differentiating with respect to theta, we have this second order derivative. and substituting in the polar form of the differential equation of the path, that is in this equation, we have very simple calculations. We have f varies as 1 by r to the power 7. So this is the law of force. So students should try for the third problem, where the equation of the curve is given by r to the power n equal to a to the power n cos n theta. You should try for this, you will get the law of force. In that case, you should try this. Next, we talk about a special problem. I will give you a hint of this problem, how to solve with this problem. Go through the problem first. A particle of unit mass describes an equiangular spiral of angle alpha under a force which is always in a direction perpendicular to the straight line joining the particle to the pole of the spiral. Show that the force is this. So you have to prove the force is this, and the rate of description of sectorial angle about the pole is this. So we talked about a sectorial angle, that is a dot. So first let us see the spiral. Yeah, this is the spiral. OX is the axis, O is the center, and P is the position of the particle, F is the force in that direction. So what is the equation of motion of the particle? First question is that equation of motion. We have to write out the, there are two directions, radial and cross radial direction. So we have to write out the two equations of motion. One is the radial direction of equation of motion, another is the cross radial direction of motion. So what is the radial direction of motion? Equation 1 is, there is no radial direction, there is no component in the radial direction, so it is 0. R double dot minus r theta dot square equal to 0, and in the cross radial direction you have 1 by r ddt of r square d theta dt is equal to f. So equation of equiangular spiral of angle alpha. What is the equation angle alpha? You know that equiangular spiral is given by this equation, r is equal to a e to the power theta cot alpha. Here alpha is this angle, this is the alpha. Now taking log on both sides, you have d theta dt. After differentiating with respect to time, substituting in 1, you have d dot d theta dr dt. I am not going into detail of that calculation, you can easily do it. I am just giving you the hint for how to solve with this. From 3 you have d theta dt, and finally 2 becomes, after some manipulations you can go through it, this is the final result. This is you have to prove, and this is already proved. So you go to the second part and try this for your solution. In that case it will complete. Next, lastly, today's lecture, the last topic, apse. I will talk about an apse. What is an apse? An apse is a point in a central orbit at which the radius vector drawn from the center of force to the moving particle has a maximum or minimum value. Mind it. You just take a note of this. The radius vector has a maximum or minimum value. So let us describe this. Let P be the position. The same diagram, we can talking about the same diagram. Now at an apse, R will be maximum minimum. So what is the relationship between U and R? U is equal to 1 by R. So U will be minimum or maximum. And what is the conditions for maximum minima? First derivative with respect to theta equal to 0. So du d theta equal to 0. That gives you 1 by P square from this relation. 1 by P square is equal to U square, and 1 by P square is equal to 1 by R square. So finally you have P is equal to 1 by R. So what is P? P is the perpendicular from O to the tangent line. So the length of the perpendicular is equal to the radius vector. So this is the condition for apse. So we can conclude that at an apse, the particle is moving at right angle to the radius vector. And also we discuss about apsidal apse line, the straight line joining the center of force, and the apse is called an apse line, and the length of the radius vector through the apse is called the apsidal distance, and the angle between two consecutive apsidal angle between two consecutive apsidal distances is called an apsidal angle. So let us have an example. You know that this is a very old concept. If this is the position of the sun and this is the position of the earth or any planet, you know that these two nearer to the sun is called perihelion. This is the nearer to the sun, and this is the position farthest from the sun, so this is aphelion. So this is the example of apses. So I conclude my topic today. Thank you all.